Welcome everyone. My name is John McCartney and I am the session chair of this session together with Yoe Zek. The session is titled Ground Improvement and brings together papers on a range of topics where geosynthetics are used to improve the behavior of natural and compacted soils. A couple of things to note before we start the presentations. You'll have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other educational session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code shown in the session to verify that you did attend the session and ensure that you receive the proper credits. Please enjoy the presentations.
Hello. This presentation shows highlights of the paper entitled High Vertical Loads on Soft Foundation Soils Improved with Rigid Inclusions and Geosynthetic Reinforced Load Transfer Platforms, which was authored by Lilma Ribeiro Shimon, Engineering Department Head at Husker, and Alex Potter-Waite, Regional Design Manager at Menard Group. We thank you for your interest on this topic. Designers and builders are aware of the difficulties encountered to develop construction on soft soils. The challenges are due to, among other things, the low strength and lack of bearing capacity of weak soils. There are many techniques that allow for the safe construction and good performance of structures built on weak soils. Among them is the use of rigid inclusions called controlled modulus columns or CMCs, which are topped with a load transfer platform reinforced with geosynthetics capable of developing very high strength at low strengths. On this paper, the reinforcement type under discussion is a high tenacity polyvinyl alcohol woven textile, PVA textile. This slide shows the main elements that comprise the system. The CMCs, vertical rigid inclusions, which are robust ground improvement elements installed using a displacement tool, and a thick load transfer platform made of compacted granular material reinforced with a high tensile modulus PVA reinforcement. Together, these elements improve the stiffness of the ground, transferring the load of the structure through the soft soils into a competent bearing layer. The bearing capacity is increased and the long-term settlement is reduced. The paper discusses each of the elements, providing more detailed information about the CMCs, the geosynthetic characteristics important for a good performance of the load platform, and 2 case studies. A quick summary of the sessions developed on the paper are presented on the next few slides.
Hi everyone, I'm Alex Potter-Waite from the Menard Group. For those who don't know, Menard is a design-build contractor specializing in ground improvement techniques such as rigid inclusions. So just a quick overview of what a rigid inclusion is. Basically, it consists simply of a column of grout or concrete, which is typically displacement drilled and usually unreinforced. The inclusion is installed through soft soil into a deeper bearing layer to attract a high percentage of the overburden load and transfer it below the compressible layer and into more competent layers at depth. The technique was developed in France in the 80s and brought to the US by Menard in the early 2000s under the trademark name Controlled Modulus Columns, also known as a CMC rigid inclusion. Some typical parameters: diameters between a foot and a foot and a half, loads between 60 and 200 kips, and depths as deep as about 150 feet. Few features of the rigid inclusion system. First, the displacement drilling method brings up very little spoil, which not only makes for a tidy working platform, but can also be very beneficial for contaminated sites. Compared to a more flexible inclusion, such as an aggregate pier, rigid inclusions can typically handle higher loads and meet stricter settlement tolerances. Also, they won't bulge out or lose capacity in very soft or organic soil, so they're a great option for peat deposits, for example. And finally, they're often used in karstic environments where the low mobility grout can actually be used to fill some small to moderate voids as well. So I've introduced what a rigid inclusion is, but the columns themselves are just a part of the overall ground improvement system, and each of the parts must interact properly with each other to achieve optimal performance. So first of all, you have the structure or the embankment that needs to be supported. That structure is going to interact directly with the layer known as a load transfer platform, or LTP. This layer efficiently transmits the structural loads into the grid of inclusions below, and we'll be talking more about this later in the presentation. The inclusion design should be optimized to vary the spacing, diameter, embedment length based on site constraints and the load transfer platform thickness. And one thing I'll add is that the soil structure interactions involved within this system can become fairly complex, so advanced design methods are recommended, such as finite element modeling, and Luma is going to touch on that in a little bit. Zooming in on the load transfer platform, it's usually composed of a well-compacted granular material, often a dense graded aggregate or DGA. Alternatively, it could be a less select material such as sand, silt, or even clay if it's treated by some sort of lime or cement binder. The LTP often includes geosynthetic reinforcement, which can serve several purposes for the design depending on the situation. The geosynthetic can enhance stress transfer into the inclusions, improve global stability and bearing capacity, reduce the overall thickness of the LTP, and act as a lateral restraint for the system. And now Lilma's going to talk a little bit more about load transfer platforms and geosynthetics.
There are multiple methods for designing the load transfer platform and for obtaining the geosynthetic reinforcement requirements. Some of these methods are too simplistic and can greatly underestimate the required resistance of the reinforcement. The paper shows that the most reliable methods are the British and the New German methods. These verify the tensile stress condition of the reinforcement under different requirements: load distribution due to arching, lateral spreading, and extrusion. The reinforcement increases the overall stability of the embankment and allows for grading spacing of the CMCs. Both methods also agree that it is important for the designer to minimize the number of reinforcement layers through the use of high-strength materials. This is to avoid uneven distribution of stresses, eliminating the risk of overstressing and failure of the geosynthetic. The deformation and stresses on the columns must also be verified. Due to the complexity of interaction among the elements, that is, between the embankment and the platform, between the platform and the reinforcement, between the platform and the soft soil, between columns and soft soil, and finally between the columns and the end-bearing soil, provides the need for an analysis using finite element methods, which is strongly recommended. Geosynthetic reinforcements are manufactured with different raw materials or polymers. For example, aramid, polyvinyl alcohol, polyester, polypropylene, and polyethylene. Different polymers result in different mechanical behaviors, including stress-strain curves. The tensile modulus of the reinforcement is very important, since failure can occur not only due to the lack of tensile resistance, but also due to excessive deformation of the structure. Therefore, the strength as well as the allowable deformation should be specified for reinforcement applications. Here, we see that materials like aramid, polyvinyl alcohol, and polyester have much higher modulus than the others like polypropylene and polyethylene. Notice the steeper lines in green color versus the red ones, which represent higher modulus for the green lines, much lower modulus for the red lines. Therefore, materials like aramid, polyvinyl alcohol, and polyester are suitable for this application, reinforcement, while the others are not. Creep, which is the accumulation of deformation of the reinforcement under constant load, is also a very important characteristic of the geosynthetic and must be considered during design and included on the material specifications. These graphics show the typical curves for accumulated strength through time for high-density polyethylene and polyester materials. HDPE is not suitable for this kind of application due to its large long-term deformation that can cause excessive movement and failure under the service limit state of the structure. Materials like polyester, polyvinyl alcohol, and aramid have much lower creep and are used for this kind of applications.
All right, one quick case study to wrap up. This is a project that's currently ongoing in Toledo, Ohio for ODOT. It's the new DeSalle Bridge carrying I-75 across the Maumee River. It involves about 5,000 CMC rigid inclusions and almost a million linear feet of PVDs or wick drains installed under both bridge approach embankments and MSE walls. Quick overview of the site. In pink on both sides of the bridge are the wick drain areas. In those zones there were no rigid inclusion supports and the wick drains were used simply to accelerate the settlement of the embankments prior to paving. In light blue on the right side, which is the north approach, were CMC rigid inclusion zones to support the tallest retaining walls and embankments on the project in excess of 40 feet high. Finally, in red on the left side at the south approach is the area I'm going to focus on for this case history. In that area, CMC rigid inclusions and wick drains were designed within the same area in a unique soil profile known as rouge. So looking at that soil profile on the left, I've included a representative boring log. On the left of the log is the SBT N value, and on the right is the moisture content. And you'll notice one thing right off the bat, which is that they don't seem to match up. You've got some very high N values with some very high water contents. Normally the wetter the soil, the softer it is, but it wasn't the case at this site. So that's that rouge material that I mentioned, which is a name for a local soil layer that is formed based on dumping of byproducts from the glass-making industry in Toledo, which was very big at one time. It's probably closest to an elastic silt, but it basically cements into a hard material until it is sheared enough to basically liquefy and lose nearly all strength. So not a great material to build a bridge approach over. The DOT originally spec'd this part of the site for deep soil mixing. The issue with that was not only it would have been difficult to get the mixing tools to even get through it, but then you have to account for potentially high variability in the end product because the initial fill is so variable. So Menard proposed an alternate solution to effectively bypass the rouge layer with a grid of CMC rigid inclusions. Then, because there was concern that the installation method itself would cause some loss of strength, the wick drains were added to quickly drain away any excess water without causing long-term settlement. And you can see the final typical detail on the right with the grid of inclusions, the wick drains in between the inclusions, the load transfer platform, and the MSE retaining wall above. So for most of the areas at the south approach, there was actually no need for the geosynthetic within the LTP due to the high shear strength of the rouge, as long as it wasn't overly disturbed. However, in one zone there was an interesting phenomenon occurring in the design phase due to a retention basin in front of one of the walls. As you can see from the geometry, the slope in front of the wall took away some passive resistance compared to a flat ground scenario. So what happened is that in the FEM analysis, the wall tended to slide down into that basin rather than simply move straight down onto the bed of rigid inclusions. Now, that deflection could have not only caused issues with the wall panels, but also the perimeter inclusions would have been overstressed, which would only exacerbate the issue, and potentially add additional settlement into the mix. As a result, a lateral restraint was required to tie back the wall into the rest of the embankment. This material had to have very high stiffness in order to attract enough load from the wall, and ultimately a Stabilenka Extreme material was selected with a stiffness of approximately 2,000 kips per foot. And I thought this was an interesting example of a unique application of a robust geosynthetic under some really high loads. Finally, a few notes on the construction, and you can see a picture of a few of the drill rigs on the site there. The majority of the inclusions were installed in 2019 and 2020 with a final phase planned for later this year. I wish I could say that the drilling of the rouge layer went well. As it turned out, the material really stayed cemented for the most part. It was really difficult to drill, but the first phase did eventually get finished in early 2020. As for the geosynthetic, the installation went smoothly. As part of the design analysis, we actually studied a rebar mesh as an option for the lateral restraint. But ultimately, the geosynthetic option was selected mostly due to the ease of installation and since it kept the overall project on track. There's actually another retention basin in the last phase that still needs to be addressed, possibly with something similar. I want to thank everyone for listening. I hope this presentation and the associated paper were informative, and enjoy the rest of the conference. Bye.
Thank you for listening in today on my presentation on economical solutions for solar farm development. Solar power is becoming more affordable in the United States, along with other alternate energy solutions such as wind. I bet you've started to see them popping up in your neighborhood or on a recent drive. Although these systems have become more cost-effective, there is a driving need to reduce the costs associated with development and maintenance of their facilities. Typically, rural and often undesirable land is selected for solar site development due to affordable land costs. Following contractor selection, construction activities over these unsuitable soils present many challenges. Many times, the selected project site requires stabilization to improve bearing capacity. Whichever method is selected to stabilize the area, it needs to be a long-lasting solution, which can stand the upfront construction impact, as well as provide long-term support for traffic, loading, and environmental impacts. In a lot of the solar projects that I've worked on, unsuitable soils are the driver for increased and often unbudgeted costs. This happens because the process of purchasing land, going through a very long permitting process, to finally contractor selection, this can take years. And then whether or not an upfront geotechnical investigation was completed could have been completely overlooked. High-strength geotextiles have had a long history of successful performance for stabilization with our civil structures. And in going through what type of geosynthetic we will use, we are often considering the following functions. After all, the product that is selected and then buried becomes a long-lasting component of the system. Typically, we need all of these functions to work in unison to have successful application for long-term support. There are tons of different products on the market from different suppliers and manufacturers. I always recommend getting the manufacturer's representatives involved so that they can help you through the process of selection, design, and installation. Different products have unique requirements for successful performance. In the half dozen or so solar farms that we have worked on, I have found the following items extremely important for consideration throughout the process of evaluating stabilization methods. Installation from a constructability and also a long-term performance standpoint are important. So each of these will be independently touched on during the case studies. As far as evaluation of soil properties and weather events, consider that saturated soil can have a big effect on the bearing capacity of the subgrade soils. Installation of the geosynthetic and first lift of aggregate could pose challenging for certain soil types following rise in moisture content. Look at the California bearing ratio, CBR, shown on the screen for 4 soil samples on the chart. The strength is shown to decrease rapidly during the first 24 hours of wetting, and it continues to decrease at a reduced rate followed by the initial wetting period. Sometimes, depending on where a project is located geographically and when they plan in the year to stabilize soft soils, I often provide the project team with both a dry weather and wet weather section. There are some products or adjustments to section thicknesses that may be required for successful installation in less than ideal circumstances. Another item to consider is contamination of the aggregate layer. It is quite typical that the roads on a solar farm would remain unpaved. And although using a geotextile to act as a separator between the subgrade soils and the import aggregate would minimize this possible contamination, due to cost, it's often overlooked the whole process from start to finish. So the roads are treated with a geosynthetic, but the other areas aren't. And what this can lead to is contamination of things like equipment that's accessing the untreated sites, eventually using the roadways and causing contamination from the top down instead of from the subgrade up into that unbound aggregate layer. So we'll actually look at this a little bit in a study later. Just note that even just a small amount of fines contamination can have a significant impact on the modulus and the bearing capacity of the aggregate layer. So when we're bringing in that whatever thickness is calculated to as required thickness to stabilize our section, we want to maintain the integrity of that layer and not have fines intermixing there. The three common methods to stabilize soil are the remove and replace, mechanical stabilization with geosynthetics, and chemical stabilization. So in the remove and replace method, this involves undercutting and removing soft, weak, or possibly wet, undesirable soils and replacing it with an engineered fill. For mechanical stabilization with geosynthetics, the geosynthetic is placed on top of the subgrade or subbase, or under or within the aggregate layers, and works with the soils and aggregate to create a reinforced composite section. And lastly, chemical stabilization, which is commonly lime or cement, is the process of altering properties of soil by changing the gradation through mixing with other soils or chemicals to improve strength and durability. The remove and replace method is usually costly and may not address the problems at hand, because sometimes when we excavate through the weak surface soils, we expose even lower strength soil, and this also has the potential to interfere with groundwater. Additionally, depending on the project's cut and fill requirements, removal of excavated material and importing select fill can prove to be costly and time consuming. For solar farm projects, I would say this is certainly true. We often see that the haul distance for import and export is substantial, adding to construction schedule and cost using this method. For chemical stabilization, mostly this just improves the short-term strength and bearing capacity, and can also help with some of that shrink and swell behavior. However, durability issues is the major concern, as well as potential health issues. This method is certainly the most time-consuming and weather-dependent, but really what we see is that you begin to experience a breakdown in structure very soon after hardening. So this might be okay where you just need a temporary platform to construct a pad or a road, but you may not want to depend on the durability of your chemically treated subgrade throughout a long duration of use. And then, of course, for certain soil types, for example, sulfates that are present with lime stabilization, reactions between naturally occurring ground elements, and the chemical additives could be detrimental to the durability of the stabilized platform. In addition, this method requires a unique mix design, cure time, and the results after all of that are still highly variable. Geosynthetic stabilization enhances the performance of the section, enabling the contractor to use less stone, and provides a reduction in thickness or complete elimination of undercutting of in situ soils. Unlike chemical stabilization, no special equipment is required to place and install the product. There's no cure time, and following compaction, the geosynthetic stabilized roadway can be immediately trafficked. This solution becomes a permanent structural component of the system. Now let's take a look at two case studies using high-strength geotextiles for soft soil stabilization. The first project is the Chico Energy Center, located in Southeast Arkansas, and this is Arkansas's largest utility-scale solar energy project. It's located in the southeast corner of the state near Lake Village, and the Energy Center will span 825 acres. As mentioned previously, a lot of times with energy projects, a common theme is affordable land space, so we end up with these challenging soil conditions. Specifically for this project, the area that was developed used to be rice fields, Cultivated rice is extremely sensitive to water shortages. To ensure sufficient water, most rice farmers aim to maintain flooded conditions in their field. If you can imagine this area that has been flooded both by nature and man for several decades, it does not translate into an easy-to-construct facility. Typical conditions across the project during dry site conditions are shown here. Due to the fat clays with low permeability, it was common during the 12-plus months of construction for the site to be in flood conditions. During the design phase, we were contacted to be a part of the project team to evaluate ground stabilization options to benefit project performance, specifically for access roads and material staging areas. Working with the design engineer, they provided all the necessary information needed to evaluate the thickness of aggregate required above one of our high-strength products in order to support their intended loads. Solar farms don't typically have very heavy loading like we see on wind farms due to the large components. So typically the largest and heaviest loads we see are during construction of the roads themselves. Our solution needed to provide separation and filtration between the poor subgrade soils and the import aggregate, also hold that aggregate in place, that's confinement, and provide long-term reinforcement. Using Giroux-Hahn methodology for unpaved roads, we can calculate the required thickness of both the unreinforced and reinforced sections. The project team elected to choose the solution which provided the largest cost savings. This was a 46% reduction in cost by using a high-strength geotextile and reducing the required aggregate. I'm going to show you some areas that aren't treated, followed by some areas that are. At one point during the project team even thought about having to install the solar panels off of a floating barge because of how much rain they were getting. These are the pathways through the solar panel arrays that were not supported with geosynthetic stabilization. Now compare that to this roadway that was treated with a high-strength geotextile and 7 inches of aggregate fill. I mentioned that construction sequencing was very important. So when the pile driving operation stayed ahead of the road construction, everything was going well and the 7-inch section maintained support. But as the roads got ahead of the pile driving operations, they needed some more sacrificial thickness due to the pile driving machinery tracking up that sticky clay onto the structural section of the roadway and pulling it away. In some places, the geosynthetic was exposed due to the unanticipated use by the pile driving equipment. We achieve continuity when the road is wider than the roll width by overlapping adjacent rolls of fabric. And then on this project, some additional thickness was brought in so that that 7-inch structural aggregate always remained intact despite additional road usage by the piling rigs. In the end, we were able to treat very challenging site conditions with this mechanical treatment, and it also provided cost and economical reduction. Mentioned earlier, limiting the required over-excavation and import aggregate decreased section cost, leading to a $560,000 savings for the 70,000 square yard area. In addition, this reduced CO2 emissions due to less hauled material, less trucks, and less emissions produced during site construction activities. The second project we have today is the Impact Solar Project that is located in Lamar County, Texas, not too far from Dallas and just southeast of Paris, Texas. And yes, there is an Eiffel Tower in Paris. Not entirely different from the site we saw earlier, just less water here. The site also had some pretty poor soils to construct roads over. They tried lime stabilized previously, and unfortunately that method did not provide the anticipated performance, and they were having loss of support relatively early after the application. This site was comprised of clays, which held up okay when dry, but turned to mush when wetted. At the end of this project, the roads would be turned over to TxDOT and part of the area roads infrastructure system, so the roads needed to be built to last. We reviewed the geotechnical report and also confirmed in situ strength through dynamic cone penetrometer DCP testing. The soft areas of the site had a CBR between 1.5 and 3%. The section included 6 to 8 inches of aggregate over a high-strength geotextile. This system works because of the subgrade soil reinforced aggregate interface through friction, and the proof is in the pudding here with pictures of side-by-side performance of the reinforced versus unreinforced trafficked areas. This project presented an enormous cost savings of $3.2 million for the 13 miles of road that were stabilized. Here today, we have seen 2 successful deployments of high-strength geotextile to support solar farm access roads constructed over soft, unsuitable soil. These solutions were cost-effective, deployed easily, and on top of monetary savings, also provided a decreased environmental impact. If you have any questions, please feel free to reach me by email or phone. Thank you for tuning in, and I hope you enjoy the rest of the sessions at the 2021
Hello, I'm Radhavi Samarakon, and I'm a PhD candidate working with Professor John McCartney in the Department of Structural Engineering at University of California, San Diego. I will be presenting our paper on performance of prefabricated thermal drains in soft clay. To begin with, I will give a brief introduction about the background and motivation for this study, followed by a description of the numerical model. Then I will discuss the main observations made when using a prefabricated thermal drain, and finally, the concluding remarks. Construction in soft clay poses challenges to geotechnical engineers due to their undesirable properties such as high compressibility and low shear strength. Prefabricated vertical drains, or PVDs, are widely used for ground improvement when encountered with soft clay deposits. Here I have shown an instance where PVDs are used in a ground improvement application, and the figure below shows a PVD consisting of a perforated plastic core wrapped with non-woven geotextile. However, there are still challenges when using PVDs, such as maintaining stable embankments, the cost, time for primary consolidation, and low hydraulic conductivity in the smear zone. So more recently, the use of thermal PVDs has been investigated as a method to overcome some of these challenges. A thermal PVD combines a conventional PVD with a geothermal heat exchanger. This can be achieved by using closed-loop plastic tubing, circulating heated water within or around the core of a conventional PVD. At the bottom, I have shown a schematic of a study conducted in Thailand where thermal PVDs were used in combination with a surcharge in a field-scale experiment. In this study, an increase in the magnitude as well as the rate of settlement was observed when using thermal PVDs. These increases are attributed to the thermally induced excess pore water pressure, increase in the hydraulic conductivity of the pore fluid, and thermoplastic contraction observed in normally consolidated clays when the soil is subjected to an increase in temperature. Another advantage of using thermal PVDs is that they can be used for geothermal heat exchange or underground heat storage after ground improvement. Although thermal PVDs have been tested in proof-of-concept field experiments, there are still several variables and soil behavior that need to be characterized better. With that in mind, the main objective of this work is to simulate coupled processes of heat transfer, fluid flow, and volume change in saturated, normally consolidated clay layers with different mineralogies. Specifically, we considered clay layers of kaolinite, illite, and smectite. We considered a finite soil domain based on the large-scale odometer experiments of Art Diang et al. A thermal PVD was located at the center, causing axisymmetric radial flow and one-dimensional vertical consolidation. Using this geometry, representative of a large-scale odometer, a 50 kPa surcharge load and an increase in temperature from 25 degrees to 90 degrees Celsius were applied simultaneously. We maintained a constant temperature boundary at the drain and a convective boundary at the outer edge. Drainage was permitted only at the thermal PVD. The initial porosity of the clay layer was 0.5 and radial strain at the outer edge was considered to be 0. The figure at the bottom shows a typical settlement profile along the radius. This can be expected to vary because of the non-uniform temperature profile along the radius. The results presented in the following sections will be at a midpoint along the radius, representative of an average value. To model the coupled processes, heat transfer was modeled using the Fourier's law and energy conservation principles. If you look at the top set of equations here, T is the temperature, R is the radial distance, rho sub S is the density of the soil, and C is the specific heat capacity of the soil. The change in thermal conductivity, lambda sub T, with porosity N, was also accounted for using a parallel model. This increase in temperature will impact the fluid flow by thermally induced excess pore water pressures and increased hydraulic conductivity. Fluid flow through the porous media was modeled based on principles of mass conservation and Darcy flow. In the second set of equations here, U is the pore water pressure, K is the intrinsic hydraulic conductivity, and alpha sub W is the thermal expansion coefficient of water. Change in fluid viscosity, eta sub W, with temperature was accounted for using an empirical relationship. Volume change in this case will consist of two parts. Volume change from mechanical loading due to the surcharge can be obtained using the compressibility relationships, where E is the void ratio, sigma prime the effective stress, and lambda the slope of the VCL. In addition, thermoplastic volumetric changes will be generated as a result of the elevated temperature. A relationship by Lalui and Sekrovec was used to obtain the thermal volume changes. The gamma here is a material-specific parameter. For the loading conditions in this analysis, the total stress will remain constant, and the changes in effective stress due to a change in the pore water pressure can be obtained from Tersagi's effective stress principle. The focus of this study was on the thermal behavior of kaolinite, illite, and smectite. The material properties of each clay type was obtained from literature as shown in this table. All three clay layers were maintained at 0.5 initial porosity. Due to the different mineralogies of each clay type, they have different material-specific properties. Out of the three clay types, kaolinite has the highest hydraulic conductivity and smectite the lowest. Here I have shown the results for radial heat transfer through kaolinite, illite, and smectite. The different lines in these figures correspond to different radial distances from the thermal PVD. The solid line is the closest to the drain, and the dotted line is the farthest from the drain. And it can be seen that locations closer to the thermal PVD have higher equilibrium temperatures, and as you move away from the thermal PVD, the equilibrium temperatures are lower. Moving on, here I have the results for excess pore water pressure generated. The results at 25 degrees Celsius, the dotted line, represents a conventional PVD, and the results at 90 degrees Celsius, or the solid line, represents a thermal PVD. For kaolinite, there is no significant increase in thermally induced excess pore water pressure. On the other hand, for illite and smectite, which are the slower draining soils, we observed higher magnitudes of initial excess pore water pressures when a thermal PVD was used. However, for all three clay types, the excess pore water pressures dissipated at a faster rate when using a thermal PVD compared to a conventional PVD. As we discussed in the numerical model, when using a thermal PVD, there will be mechanically as well as thermally induced strains. These figures show the time series of normalized settlements for kaolinite, illite, and smectite clay layers. To re-emphasize, the dotted line represents a conventional PVD, and the solid line represents a thermal PVD. We can observe an increase in the magnitude as well as the rate of settlement for all three clay types when using a thermal PVD. An interesting observation we made was the slight initial expansion in illite and smectite clay layers, which are the figures shown in the middle and the right here. And if you recall, we observed thermally induced excess pore water pressures also in these two clay layers. So we investigated this a bit further by looking at the clay behavior at different temperatures. The figures here show the results for smectite, focused on the initial period during consolidation. The top figure shows the time series of the normalized settlement, and the bottom one shows the corresponding excess for water pressure profile. You can see that the magnitude of excess for water pressure generated increases with increase in temperature, and correspondingly, the observed initial expansion also increases with temperature. However, as the clay layer continues to drain, the excess for water pressures dissipate, and finally, we get net contraction for all the clay layers. To look at the effect of hydraulic conductivity on the performance of a thermal PVD, we looked at kaolinite layers at different initial porosities. Here I have shown the settlement curves for a kaolinite layer with 0.43 initial porosity and 0.67 initial porosity. We observed a slight initial expansion in the clay layer with the low initial porosity, which means that it would also have lower hydraulic conductivity compared to the clay layer with higher initial porosity. This is similar to the observations we made with illite and smectite at 0.5 initial porosity, which also had low hydraulic conductivity. In conclusion, simulation of thermal PVD operation on saturated normally consolidated layers of kaolinite, illite, and smectite shows that soil thermal and hydraulic properties play a critical role in thermal soil improvement. Thermally induced excess for water pressures and a slight initial expansion were observed for the slow draining illite and smectite layers, but not in the fast draining kaolinite layer. However, net contraction was observed for all three clay layers. Clay layers with different hydraulic conductivity values showed a similar increase in the magnitude of settlement, but different rates of settlement. Further investigations can be carried out on the interaction between multiple PVDs in the field to optimize the applied temperature and drain spacing requirement. I would like to acknowledge the National Science Foundation and the Department of Structural Engineering at UCSD for supporting this research. Thank you.